This is the sweetest theme music in the world. Hey there. We're talking about projectile properties of flight. And whenever we're talking about this, what we mean is that we, hit something or we throw something or shoot something out of a cannon and it's in the air. And we're going to talk about air not really existing here. We're getting rid of air resistance. But we're going to talk about in this video some common projectile motion characteristics that exist. Some of the things that we need to think about as an object is moving along its path. And if you're solving a problem in the world of physics regarding projectile motion, there's no set way to solve a problem. It's not just like use this equation every time and you're good. You're going to have to recognize what do you have in the problem, what are you given, and then you have to make the right decisions from that. And in a few more videos, we'll get to something that I call the box or the projectile box, which will really help you identify what you have and what you can do to solve things out. But for right now, let's just talk about some interesting things that we'll see whenever we have projectile motion. So on the left here, we have what's known as PHET, P-H-E-T. It's the projectile PHET simulation. It's got a little cannon here. There's a little Da Vinci down here, a little target, and we see that if I fire off a rocket or some cannonball, it will fire, and we'll see the path, and the cannonball will smack the ground or the road or whatever it is. Okay. Now, what we're going to do here first is when you have an object, arcing through the air like this, there's a few things we see. One, it's a nice symmetrical approach to this. So just like we saw with just vertical motion in Unit 3, however long it takes for an object to get to its maximum height, that's the same amount of time it's going to take for it to reach the ground again, assuming there is no air resistance. And we are getting rid of air resistance in this class. It makes things, much more complicated. If you did have air resistance, it would actually take you longer to fall back down. You're going much slower. But no air resistance, same amount of time, okay? We actually have symmetry, halfway through this, this path here. Now, one of the things that is kind of weird when talking about projectile motion is that the x velocity and y velocity are independent. They have nothing to do with one another. So let's just fire this cannon again, and we'll take a look at the velocity vector and then the acceleration vector. So fire. And let's just watch that again, then pause it. So in yellow right here, this is our acceleration. And let's just look at the yellow acceleration vector the whole time this thing is in flight. As this thing is moving, that yellow acceleration vector, it's not changing. The yellow is always the same. It's just the same amount pointing down. And that makes sense because that yellow acceleration vector, that's gravity. And gravity isn't changing as this object moves. Okay? So as this object is moving across its path, gravity's still gravity. It's always pulling it down. Now, what is changing here, if we fire the cannon, is notice how the y velocity, that's this green vector, the y velocity is changing. It started very large. It's very large right at the shot. Bang! And then as it continues to go, it's getting smaller and smaller. Well, that's because if the velocity's up, but gravity's acting down, that acceleration's opposing the velocity, it's going to slow down going up. And then when it gets to max height, that vertical velocity is 0. It's at max height. And then when it keeps going, it turns around and it begins to speed up towards the ground. And whenever it finally hits the ground, it will have the same downward velocity as it did whenever it came up. Okay? In the x direction, we see that this velocity is the exact same. It never changes. As this ball moves and moves and moves, it is not changing. The only way to change that x velocity is if you had like a booster rocket on the cannonball, and as it was in the air, it went and shot off. Or if there was air resistance, which we've already talked about. Wow. We don't have. Okay, there's no air resistance in this classroom. I've stolen all the air from you. Okay, so it's a neat thing to think about for that. So if we were taking a look at your components of the x and y velocity, the x velocity is going to stay the same everywhere. It's going to have the same length of the vector, and it's going to point in the same direction. The y velocity, though, it'll start large, begin to get smaller, zero out, and then it'll flip directions. And if it's at the same height, it's the same amount. So if this was like plus 10, this is minus 10, just like we saw in Unit 3. And as it continues to fall, maybe this is like minus 15, okay? So that's what's going on with our vector components. If we take a look at just like the total vectors, we'll see, and here we'll just play that through and then shoot this again. We'll see that the velocity vector in green, it's always going tangent to the path, and that tangent is like that one point that just can strike the line. You know, we talked about this in class. If you had a circle, you know, what's one line you could draw that passes through that red point that doesn't go through the circle? Well, that's the tangent line, and that's a poorly drawn tangent line. We'll try that one again. That's a tangent line, just like that. Okay, so this green line right here, that's a tangent line, and as we step through this and watch this move, we see that that velocity vector is constantly changing. When it gets to the max height, that velocity vector is perfectly flat because it's only the x velocity here. The y velocity is 0. And this velocity vector, if we actually take a look at it, it is the addition of the x and y vectors. So if I kind of look at the components real quick, if I add up the x and then go down some amount of y, so if I move this y vector over and I go down that amount, that is this velocity vector. The acceleration vector will always just be pointing down because there is no other force acting on this in order to change anything. Notice if I hit air resistance, it's going to push backwards because it's going to, you know, be pushed away a little bit. So air resistance, get rid of it. No, don't want it. It's just pointing down. Okay. So if we think about acceleration, acceleration for us is always going to be acting down by the same amount everywhere. Our velocity vector can change a little bit. Up top, it's perfectly flat, but it's always going to be tangent. Oops, that should be longer. It's always going to be tangent to the path our object is taking. Okay, so those are just some things to think about. It's also important in these projectile motion problems, as you're kind of thinking through them, you need to choose positive and negative directions. Traditionally in physics, we call up positive and down the negative direction. That's just kind of classical thinking, which will mean that your acceleration, which is gravity, will be some negative 9.8 meters per second squared. So that's something to think about as you're working through problems. Don't forget that negative. It also means that if you have a problem kind of looking like this, where you start high and end low, your displacement here, your delta x, or some people call this a delta y in the vertical direction. Some people call this delta x, and then, you know, up and down, they would call that delta y. I'd like to call just everything delta x, a displacement, and you'll see why later on. But this would be some negative number because you're falling down here. So just keep your positive and negatives in check as you're going through some things. But other than that, these are just some things to think about what's going on with projectile motion. The vertical velocities are changing, but the x velocity is staying nice and constant. And you see this in your daily lives. If you ever played sport before, you know, if you're playing baseball, the pitcher throws the ball, and while the ball is dropping, you like know when to swing the bat because the ball is moving towards you at a constant rate. You know, if you're throwing a football and playing catch, like, you know where to run to. Your brain's running like thousands of these processes every second in order to just find things. And, you know, if you are tossing a ball back and forth to yourself like this, you know where it's going to land because, you know, your brain's seeing a bunch of projectile motion. It knows the x velocity is constant, and you can read acceleration pretty well with your eyes. So that's just what's going on there. Okay, so nothing too crazy. In our next video, we'll talk more about some projectile motion concepts and other things you need to think about, and then we'll get into the projectile box, and then we'll talk about some practice problems. But until then, we are finished here. Adios, and you take it easy.